Good afternoon, everybody. This afternoon, our speaker is Dr. Bilge Demirköz. She is an associate professor at Physics Department. Dr. Bilge Demirköz received her BS and MS degrees from MIT after graduating from Robert College of Istanbul and followed that up with a PhD from University of Oxford. After being a CERN fellow, she continued her postdoctoral studies at IFAE in Barcelona and Cambridge University. Demirköz returned back to Turkey 4 years ago to aid in the process of Turkish membership to CERN and continues her research at the METU Department of Physics and at CERN. She has worked on the construction, commissioning, and data analysis of ATLAS experiment at the Large Hadron Collider and the Alpha Magnetic Spectrometer on the International Space Station. With her team at METU, she is working with her team at METU, she is now working on looking for hints of dark matter annihilation from the galactic halo and performing a measurement of particle radiation in lower orbit. Thank you very much for being us, for joining our program. Thanks a lot.
Thank you. It's a great pleasure to be here. I gave one last year. It's going to continue some of the same slides, but a lot of it will be different. We're all very excited, of course, about gravitational waves, as we should be, because until now we never looked at the universe in gravitational waves. We looked at the universe in different things. For example, gamma ray bursts. Gamma ray burst was one of the first signals for looking out to the universe. Out, I mean, not just, some stars in our local vicinity, okay? When you look out at night, you see stars that are very local in the galaxy. Say, okay, where is the closest star? Besides the sun, after the sun? Anybody? Alpha Centauri, and do you know how far away it is? 4 light years. 4 light years. So when you look at the back, you're looking back into the history of the universe when you look up into the sky, and all that you're seeing is light that was emitted in the past. Everything was emitted, light that was emitted in the past. If you, how many of you have seen the Milky Way? Who has seen the Milky Way? Really, nobody has seen the Milky Way. Very few people have seen the Milky Way. No, I mean, it's very shocking because my generation, we had less light pollution and we saw the Milky Way more often. I think I recommend all of you to see the Milky Way. Make some effort in the summer. Go somewhere where it's really dark and see the Milky Way. The average light is 50,000 years old. So you're looking back 50,000 years old. That's the oldest thing you're going to see with your naked eye. Okay? And if you're really, really, really lucky, and if you're on a really, really dark night, and you're at the right time of the night, I recommend you doing also this. You can actually see the Andromeda galaxy. Andromeda. Okay? Which is the closest galaxy. Okay? And if you look, and you've managed to see the Andromeda galaxy, you're actually seeing light that's 1 million years old. Okay? So with your naked eye, which is really impressive. But if you want to look further, and you want to learn more about the universe, we've always used light. And one of the things that was discovered that was really interesting was gamma ray bursts. Gamma ray bursts are these big X-ray flashes, which happen to be discovered accidentally, by the way. Okay? You might know that in the Cold War age, between Russia and the United States, both sides were scared that they would actually that they would be doing more nuclear tests. Okay? And what they did is they sent out satellites that were sensitive to X-rays and gamma rays from a nuclear detonation. And they started seeing more of these X-ray events than where there were clearly detonations. Okay? They were seeing 1 per day, which was just too much. Okay? And they were seeing them over for example, a US satellite was seeing them over the United States. And they knew they weren't exploding nuclear bombs. So then they learned, oh, actually these things are coming from the universe, these gamma ray bursts. And we have now learned that these gamma ray bursts are really interesting things where neutron stars and black holes and other, or really big suns are eating up matter from other sources, gobbling up and burping. So it's the burp of the, after eating some food, you might burp, it's that way, they say. All right, it's an analogy, it's a bad analogy probably, but that's how it is. And you can see these X-rays, and we've learned so much. We've learned that actually a lot of stars are binaries. And this was discovered accidentally. Another thing that was discovered is infrared light. We started sending out telescopes. You might know that our atmosphere, you cannot see infrared light because our atmosphere absorbs infrared mostly. So you again have to go up, either into mountains or you have to go out into satellites to observe the universe in infrared. And we've learned that galaxies actually extend more. That there's a lot of dust in galaxies. You looked at the universe with different eyes. And probably the most important discovery, I would say, that we've learned about the universe until now is the cosmic microwave background radiation. So the cosmic microwave background radiation is also known as the echo of the Big Bang. And I here use the word echo very loosely. Because echo, the word echo, implies sound. But I'm not talking about sound here, I'm talking about electromagnetic radiation. And this is a map. So what is it? It's a map of the universe at a certain frequency, 160.2 gigahertz actually, to be exact, which corresponds to a certain temperature. Okay? Black body temperature. So that's the temperature. That's what everybody says. Oh yeah, I know, the universe is at minus 270 degrees. Okay? This is the minus 270 degrees that we were talking about. Okay? And the universe is vibrating, or is radiating at this frequency. Still, it's a map. This is north, south, east, and west. Okay, so this is a map of the sky. And what you see here is you see some red and blue dots. So I would like to discuss now what does this map tell you? Okay? So the red dots are where the frequency is just a bit higher. Okay? And the blue is where the frequency is just a bit lower. So now, frequency here, okay, corresponds to temperature or energy. If you remember, for example, you had a glowing iron. A glowing iron first is red, then shifts blue, then shifts ultraviolet. Okay, it's that sort of thing. It's the same idea. Okay? All right? So the places that are red are lower energy, higher energy, hotter. Okay, the red places are hotter, and the blue places are colder. Okay? And what you see is that the dots here have a certain size. You don't see a dot that is this big. Okay, you don't see something like this. You see the dots are small. They have a characteristic size. Can you see that with your eye? All right. For those of you who are more mathematically inclined, if you were to take a two-dimensional Fourier transform with your eye, okay, you can see that there's a characteristic size of the dots. Do you see that? No? They're always, yeah, the characteristic size. Look at this size. There's a red dot here, there's a red dot there. There's no red dot like this. Okay? There's no blue dot like this. Okay? They're all the same size. The size here, the characteristic size here, turns out to be 1 degree. And that is probably one of the most important things we've learned about the universe. Somehow, the structure in the sky, in the universe, is this 1 degree. So what does that 1 degree tell you? Okay? 1 degree, when the universe started out, as an infant universe, there was really two forces that were fighting each other, okay? One of the forces was gravity. There's a lot of mass in the universe, and gravity was trying to hold all this gaseous matter together, okay? Whereas we know now that the universe is expanding, right? Everyone knows that the universe is expanding. It's actually accelerating to expand. The expansion is constantly accelerating. So, going back in time, we know that this acceleration also exists at the beginning of the universe, and this acceleration was trying to rip it apart. So if matter falls into a gravitational potential, what happens? If it falls into a gravitational potential, by falling into a gravitational potential, you get more kinetic energy, right? So what is kinetic energy? The kinetic energy is called of electrons, is called temperature. Temperature increases. Okay, that's actually the definition of temperature. Okay, the definition of temperature of U is all the kinetic energy of the electrons in U. All right, so, okay, so if these, what are these blue dots, red dots? This is the scale at which the universe was trying to hold matter together and was creating potentials big enough so that matter was falling in and heating up. Okay? 1 degree. Not 10 degrees. Okay, or not smaller. Okay, the rest, beyond 1 degree, the dark energy was winning. The energy that was ripping up the universe was winning at larger scales. At only scales lower than 1 degree, gravity was winning. So this actually gives us, the most important thing, it gives us the ratio of mass in the universe versus the dark energy that's expanding the universe. Okay? It is from this map that we now know the age of the universe. It is from this map that we now know the percentages of matter and dark matter. Okay? So you know probably that the age of the universe is generally nowadays written as 13.8 billion years. But we scientists know it too much better. Okay? And you see every year the error bar is going down. I hope one day we will be able to tell you in years or seconds. That would be an amazing thing. But I think it was going to happen. Okay? We know it to much better accuracy every year with more data. Right? And we know also the energy content of the universe from this map. We know that baryonic matter, which is matter like us, baryonic, meaning stuff that's made of quarks, mostly, okay, is 4.9% of the universe. Whereas again, this map also tells you that there is some more matter, okay, that does not interact electromagnetically. That has nothing to do with light. It does not see light, it does not interact with light, and that matter is called dark matter, and it's 26.8% of the universe. And then there is this thing, really mysterious stuff, that's called dark energy. All right? Dark energy, and that's what expands the universe. And it's not even clear that whether these three percentages stay constant throughout the universe or whether they're changing. Okay, that's a big question actually. Are these constant? Are these changing? All right. So how was this thing discovered? The cosmic microwave background radiation. It was also, like gamma ray bursts, discovered accidentally. I have a feeling all good things are discovered accidentally sometimes. Panzias and Wilson, who were electrical engineers working at Bell Labs in 1965, they were given the task of making the best radio telescope ever, okay, to observe the universe and to see the radio sky without any interference. What do I mean by that? When you have a radio, okay, you go between two channels, the old radio, think of the old radios, you would actually see this, okay, you would hear this noise, right? On your radio. Or if you go back to when you were a child and you think of the old TV screens, karlanma hatırlarsınız. Okay, the snowing white dots on your TV, if you think about it, okay? This is an electrical noise. They wanted to make a telescope without any electrical noise. So what did they do? They took their electronics and they put it inside really cold environment. Okay, they use liquid helium to cool their electronics, which then kills shock noise and all other electrical noises. And they use really excellent capacitors and excellent resistors, and they really made an excellent job. And after 1 year, still the noise didn't go away. They had this extra noise, they didn't know where it was coming from. And at some point, the story goes that pigeons came in and they nested, and they had to wait for the chicks to fly out. Okay? And they cleaned out no help staff control. Okay? And still it didn't go away. So in the end they went to Princeton physics lab, and they said, well, you have this noise, and we still can't figure out where it's coming from, but we're sort of starting to think that it's really coming from the universe. Okay? Not just anywhere, it's coming, we just can't figure it out. And the person told them, yes, you have just discovered the echo of the Big Bang. So what is this? Most of my talk today is without slides, because I think it's, if you look at something, this doesn't, I try to make slides, it just doesn't work. Now, I want you to think back to the hydrogen atom. Who loves the hydrogen atom? Nobody loves the hydrogen atom. I love the hydrogen atom. Hydrogen atom is a beautiful thing. It's one of the very few unique quantum systems we can actually solve. Okay? You've probably heard about 13.8 electron volts, which is the energy that's needed to ionize an electron from the hydrogen atom. You heard about 13.8 electron volts? No? Yes. Not some of you? Some social scientists here? No? Okay? So there is an energy that is necessary to yank an electron away from the quiver. Okay? So for those of you who are engineers, probably know about this, right? 13.8 electron volts. All right. So when the universe was very young, infantile, really, okay, it was all ionized. We're kind of sure about that, okay? We were kind of unsure about a lot of stuff about the universe, but we were very sure that when the universe started out, it was all ionized. Okay, a plasma. And you've seen plasma lamps, right? You've all seen plasma lamps. Okay, so we can, okay. So for example, a neon lamp gives off a characteristic frequency at that energy level where you yank electrons from the neon. Okay, there's a characteristic frequency that corresponds to the electron levels of neon. So much like that, you can liken the young universe to a hydrogen lamp. Most of the universe is hydrogen, and most of the universe is, almost all of the universe is ionized, and as the universe is formed, it's hot and dense, but as it expands, it cools. Okay, as it's cooling, there's a point at which it drops below the temperature that corresponds to that energy level. Okay, this 13.8 electron volts corresponds to an energy level that's actually 300,000 Kelvin. 300,000 Kelvin, okay? So that's pretty hot. It's not extremely hot, but it's pretty hot. All right? And when the universe goes down below this temperature, what happens is that there is no reason for the universe to stay ionized anymore. The electrons can combine with protons and become a hydrogen atom. Okay, so all of the universe goes from being ionized to being neutral. Okay? And this photo is that moment. It is called the last scattering surface. It is the moment at which the electrons joined the protons and became neutral. And this light has been traveling the universe for the last 13.6 billion years without actually getting much. Some of it has been lost, again, to reionization, but very little of it. Okay? And this is the light from that last scattering surface, which is the moment where the universe goes from ionized to neutral, which happens to be about 380,000 years after the Big Bang. Okay, it's not the Big Bang, it's about 380,000 years after the Big Bang. But you know, you don't remember your first months, right? So it doesn't matter to you whether it's the first month or the second month or the third month. So for us, it's pretty close to the Big Bang, right? Because we're now at, you know, we're now pretty old. Okay? We're at 13.8 billion years. So what's a few thousand years between friends? All right. So what I wanted to go back to here is looking at the universe. We've learned every time there's a new window into the universe. These are windows. This is gamma rays. This is infrared. This is cosmic microwave background. Every time we have a new window into the universe, we learn something completely new. So today, I'm going to talk about two new windows into the universe. Okay? One of them is gravitational waves, which I'm really excited about, but I don't work on, by the way. I don't work on gravitational waves. So the other window into the universe, which I'm going to talk about, is cosmic rays, which I'm really working on and I'm really excited about. So first I'm going to tell you about what I do. Okay? So I'm going to take about 15 minutes on what I do, and then I will spend the rest of my talk on gravitation. All right. So here is the International Space Station. Anybody who has seen the International Space Station? I'm looking at physicists. Oh! Shame on you. All right. So here's the thing. Can I give homework, Kojak? I give homework.
Sure, you can.
I'm giving homework.
Next
Homework
time
number
you'll give a
one.
quiz.
Homework number 1. Go see the Milky Way. Homework number 2. Go see Andromeda. All right? And homework number 3. Go see the International Space Station. Okay? These things are out there, and you can see them by naked eye. With your own naked eye. You don't need a TV or your cell phone. All right? It's a wonderful thing, your own eyes. I get really excited when I can see something with my own eyes. It's really bright. It's really big. It's bigger than a football stadium. It travels quite fast in the sky. Okay, it's going at about 8 kilometers per second. That's fast, right? Most satellites are really fast. Okay, it's really big, and it right now has 6 astronauts living on it. Okay, so there are 6 people living on it at any moment in time. And here is the thing, it's called alpha magnetic spectrometer. It is a particle detector in space. A particle detector. So what is it? It's quite big. It's about 3 meters by 4 meters, 3 meters by 5 meters by, no, 4 meters by 5 meters by 3 meters. Okay, switching from feet to meters. And about 7.5 tons. So 7.5 tons is about the weight of Trustat Alta. Okay, so it's as big as Trustat Alta. If you think about Göktürk 2, it's about 10 times.
500.
10 times.
Kilos, I think.
Yeah. Okay, so this is big by space standards. Okay, Turkey is a member of this experiment. We are a member of this experiment. It's a project of the United States Department of Energy, and it was sponsored also by NASA, so that it could go to space. So what do we do up in space? It's fundamental discoveries from cosmic rays. So cosmic rays are particles that are coming and raining down on Earth from space, and it was first discovered in 1912 by Dr. Hess. So Dr. Hess was, I think, a pretty crazy man who traveled up with a balloon to 5,500 meters without oxygen in 1912. Right? That's pretty crazy. Now it's okay, yeah? Now it's okay, but in 1912. Why did he do this craziness? He did it because he wanted to prove that radiation, which increased as you go up on mountains, they knew this. They knew that radiation levels, as you went up the mountains, was increasing. Well, some people were saying, oh, that's because mountains have more radioactive material. And he wanted to prove them wrong. He wanted to say, okay, no mountains, I just go up. Okay? No mountains, no material. So, and he proved it. He proved it using a very simple detector, actually. You know what an electroscope is? Electroscope? You know, these really dumb detector where you have these 2 plates that open up and close. You comb your hair, you put some charge, they open up. Okay? You know that. All right, you've done that experiment. Good. So he took one of these things. So how is that a radiation detector? Well, the thing is, when a particle passes through air, it ionizes the air and makes it like a plasma, a really tiny string of plasma. Really tiny, like a hair of plasma, okay? Really tiny string of plasma. So what is a plasma? Plasma is ionized and is a conductor. Plasmas are conductors. So what it does is when a particle passes through air, it makes that little cone of air a conductor so that charges can flow across it. All right? So if you have a microscope and the things are separated and you have radiation around, they will close. And how fast it closes tells you how much radiation there is. Okay? So he went up with these electroscope and had charges with it. He was charging it up and seeing how fast it decreased, how fast the angle between the two places decreased. Very, very stupid, simple radioactivity detector. All right? Very cool. So, and he discovered it. He discovered that it just kept on going up. So, cosmic rays is very interesting because most of the particles, a lot of particles we've discovered comes from cosmic rays. For example, discovery of the positron, that was huge. It was the first discovery of antimatter. Positron is the antimatter of the electron. All right? That was discovered in cosmic rays. Then discovery of pions. Pions was the first particle at the subatomic level that was discovered. Okay? It was in 1947. Then the muon, you might have heard about muons. Muons are really famous particles. There's one going through you per second. Okay? There's about 1 going through you per second. If you are up on an airplane, there's about 10 going through you per second. Alright? Muons gives you natural radiation. Alright? They break your DNA. There's no way to escape, so don't try. Alright? You can't outrun them. They're traveling at the speed of light, more or less. Alright? And muons are long-lived particles. They live very, very, very long. They live for 2.2 microseconds. That's an infinity when you consider relativity, because they're going close to the speed of light. So while they are going at 2.2, they only live for 2.2 microseconds, they can travel hundreds of kilometers because time dilation and length contraction happens. Einstein tells you that if you travel to the speed of light, you know this, time runs differently. Okay? The first place where this was discovered, you've all watched, I'm sure you've all watched Interstellar, right? Interstellar? Yeah, you've all watched Interstellar? Okay. That whole principle was proven by the muons. Right? Muons are living for very long. The ones that are going inside you right now. Hyperspace. Muons inside you. Right? So there were a lot of particles discovered. Actually, 8 Nobel Prizes have been awarded to cosmic rays. 8 Nobel Prizes. That's a lot. It's a field with discoveries. And what happens? They hit the atmosphere. They come from outer space. They hit the atmosphere and then they shower. Okay? And we're now measuring up in space electrons, positrons, protons, antiprotons, helium, beryllium, carbon. We can measure elements all the way up to iron. Okay? There's all these elements just flying in to the Earth. And we've always looked in neutral cosmic rays. We've always looked in light at the universe. Even cosmic microwave background is light. Okay? But we haven't been up there and looking at cosmic rays. So we're searching for the origin of dark matter. Okay? We know that there is dark matter around the galactic halos of galaxies, but we don't know what it is. If cosmic rays come from this galaxy to our galaxy, and what has happened is that collisions of cosmic rays produce positrons, and collisions of dark matter produce positrons. And if they get here, we might be able to distinguish them. And we might be able to distinguish a dark matter signal from the rest of the cosmic rays. So that's what we're trying to do. It's a bit tricky, but we have a tera electron volt, which means pretty damn high energy detector up there. It's a precision and multi-purpose spectrometer, and we have different kinds of detectors inside this to measure the momentum, the energy, the charge of particles flying in. Right? So what do? When a particle passes through our detector, we can actually separate positrons from the protons. Most 99% of the cosmic rays up there are protons. There's a lot of protons. So we have to separate positrons, which are really tiny particles compared to protons, away from the positrons. And our detector went to space in 19th of May 2011. All right, here is the space shuttle going up. It went from Florida. One thing I would like to say is space is really tough. One thing people don't realize is the following. When you get up, when you lift off, okay, when this thing lifted off, this was 2,008 tons. All right, and what you're trying to put in space is 7.5 tons. All right, that's a lot of fuel. Right, most of it is fuel. So what is this? This orange tank. This orange tank is filled with liquid hydrogen and liquid oxygen. You burn them directly to water. Okay? And these two rockets on the side are called solid rocket boosters, each weighing about 1,000 tons. And they burn really fast, and they actually are the ones that provide the liftoff. And in the end, you just put 7.5 tons in space. That's how it goes. Okay? Going to space is really hard, but we're going to keep on doing it. So here it is, International Space Station, and here we are out there on space. So our data goes from AMS into space, goes via the astronauts. They take care of our laptops and go up. The International Space Station goes around the Earth 18 times a day. So imagine, you have only, as it goes over Ankara, that's only 3 minutes. All right? So that's not very easy to communicate with. So what do? You actually send the data up to satellites called the relay satellites. And they are in geosynchronous orbit. And then the data bounces back. Between the three of them, these three satellites can see each other. Okay, the Earth is tiny. The geosynchronous orbit is way out. And they bounce the data between the three of them, and it comes back to Earth. It comes back to Earth at White Sands, Minnesota, New Mexico, and then it goes to Alabama, to Marshall Space Flight Center, and then to CERN, where there is the control system. Okay? The control center is at CERN. So what were we hoping to see? So as the energy of cosmic rays increases, from the collision of cosmic rays, we expect to see less positrons in space. Okay? So as the energy increases, we expect to see less positrons in space. What we see, so here is a particle of TeV scale electron going through our system. We analyze the data in two independent groups. My group is in group A. There's two groups, and we analyze the data separately. This is really important for you who want to be scientists or engineers. Okay, if you have one big experiment, what do? You divide into two. You analyze the data separately, and then you combine, whether you see whether it matches or not. And you don't talk. Okay, we don't talk with the other group until the very end. We don't talk about the analysis at all. We only come back at the end. So these are the, you see these really large error bar data that was before us. This is the positron energy, this is the positron fraction, and then we published about 3 years ago at the Physical Review of Letters, we showed we had seen very high energy positrons in space, and we showed clearly that it was going up. Okay? And compared to other experiments, we can really see that positron fraction is going up. So what now there's huge interest when I go anywhere. People keep on asking me, when are you publishing the next data point? Everybody wants to know the next data point. The reason is, if there's dark matter, okay, if this increase is really coming from dark matter, what happens is that dark matter particles annihilate, and there is only a certain amount of kinetic energy that these positrons can get from the mass of the neutrino, mass of the dark matter particle. So there is a cutoff, like here. This was the simulation. If I go back, you see the simulation, like this blue. Okay, at some point, for a dark matter particle of 800 GeV, there should be a sharp cutoff. And where this cutoff is, gives you the mass of the dark matter particle. If you know the mass of something, it's much easier to find it, trust me. Okay, that's why when the Large Hadron Collider was turning on, we were so sure we would find the Higgs, because we pretty much knew the mass of the Higgs particle. If you know where the Higgs particle is in mass, you can find it. If you don't know where the mass is, it's really hard to find it. So now everybody's asking me, okay, where it drops off. Currently, we haven't seen it drop off. Currently, it is still growing. Okay, and we're hoping to collect more data, and as we collect more data, we have a higher chance of seeing where it drops off. And when we see that drop off, I'm sure that people will be building experiments to find dark matter directly. Okay, this is an indirect measure. We're also measuring all these isotopes in space. As I told you, there are all these isotopes, right? Helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. Okay, you can count the periodic table and how much of these elements there are in the universe. The primordial components of the Big Bang, right? And we also measure how much the sun affects the environment of our Earth. Okay, the sun changes. You might have heard about this. The sun does a flip-flop every 11 years. It's like an acrobat. Okay, the sun, like you know, our Earth has a north and a south magnetic field. Okay, the sun also has a north and a south magnetic field, but it does something really strange. It flips it every 11 years. Right now, it's pointing south. In about 8 years, it's going to flip up. And then in 11 years, it's going to flip up, down. And then 11 years, 11 years, 11 years. We know that it's been this way for about 400 years. How do we know this? Well, because there has been great astronomers who keep on measuring the pimples of the sun. You heard about the pimples of the sun? You see, you know, the sun occasionally develops these black spots, like pimples. All right? And when those pimples start up, okay, the sun is getting ready to switch the magnetic fields. And we have been following the number of sunspots on the sun for the last 400 years. Okay, so we know that the cycle continues now for 400 years. Question? Okay. So here again, we can see when a solar eruption happens, it changes the number of particles around our Earth. All right? We call this a space radiation environment, and we can measure it to very high accuracy. So I worked on this experiment when I was at MIT. I helped build it. I joined it in 1999, and I worked on it until 2004. I was an undergrad when I joined the experiment, and in 2002 something really sad happened. You might have heard that there was a space shuttle called Columbia, and it exploded. It disintegrated over Texas. And when it did, our experiment was going to go to space in 2004. And NASA canceled all the flights. All right? So all of a sudden, I was a graduate student without a thesis. I hope all your PhDs are wonderful, and I hope you don't find yourself in the same sticky place. But there's a lesson to be learned from this. So I was doing joint master's and PhD programs. Okay, I finished doctorate. Okay, and I was 3 years into my PhD when it all went down the drain. So I decided, okay, I'm going to write up what I've done as a master's thesis. All right, instead of staying at MIT and starting up a new experiment, I'm going to move to Europe because I decided, okay, change of place is now necessary. I was feeling kind of depressed, and so in 2004, I moved to Oxford. I started my PhD again. I did my PhD. I went to CERN. I worked on the Atlas experiment. You might have heard about the Atlas experiment, which helped discover the Higgs particle. And I worked on it for 9 years, 8 years. And then in 2011, when I was returning back to Turkey, I heard this thing was going to go to space. So you know what I did? I went to my MIT advisor's door and I knocked. And I said, oh, I hear it's going to go to space finally, so can I come and join? And he said, of course. So that was great. It only took him 5 seconds to decide. So I thought, oh, I'm going to move to Turkey. I'm going to make Turkey a member of an International Space Station experiment. I was all very excited. I'm sure Gülseren Hocam remembers when I first arrived. I was hoping it would take a few months at the maximum to get Turkey to agree to becoming a member of this experiment. It was only asking for $4,000 over 1 year. I mean, practically we could, put the money together, all of us, right? Everybody puts in $10, you're done, right? No, it took 19 months. The thing is, you cannot all join and put the money in. Okay, the Turkish government has to say, no, yes, you can be a member of this. So it took 19 months. But in the end, now I have 3 students who finished their thesis on this and really worked hard on this. And so here's one word of advice coming from someone who's not aged much older than you. I don't feel at an age to give advice, really, but the moral of the story is, during your PhDs, something might go wrong, okay? But it doesn't go wasted. It always comes back to you. That's the moral of my story, okay? In the end, you know, it did go to space. Just 10 years late, but it did. And in the meanwhile, I did something else. And maybe it was all for good, because when I first came to Turkey and I tried to get Turkey to become a member of this experiment, people said, oh, but what good is it? You know, we only want stuff that's good for industry. So I started giving talks, I started talking about the radiation environment, not just dark matter, which I'm really excited about, and I really want to, you know, I really want us to discover dark matter, okay? But I started talking about the sun, and I was talking to people in the space groups in Turkey, and they said, okay, well, what we really need is understanding these radiation effects, because we have Göktürk 2, we have going to space, we have Alta going to space, and we want to understand this radiation environment, okay? So if you took your cell phone, your beautiful little cell phone, into space, it only works for about 6 hours. Then it dies because of radiation. Okay, average electronics equipment, okay, only stands for radiation for 6 hours. There's a lot of radiation up there. That's the bottom of the line. All right. So there are different effects. For example, a cosmic ray can come and hit a crystal in a semiconductor device and change the doping of the crystal structure of the semiconductor. Okay, and change that. Can cause latch-ups in your electronics, or burnouts, or upsets and transients. Okay? So they said, oh, can you make some calculations for us for Göktürk 2? And I said, okay. No, I mean, it's doable. Yes, of course. So I did that. And then they said, oh, but we have all this other stuff coming up. We have Alta, we have Yıldızlar Tepkidir Geri, Bilge Demirköz. Okay, we have all these new stuff that we have to produce for the next satellite. So can you make tests for these? Not just make calculations, but also make tests. And I said, okay, all right. So there is a proton accelerator facility in Turkey, in Ankara, at Sarayköy. Okay, it's close to Tayyip. Gişelere yakın, İstanbul Gişe. Okay, so and what it has is a cyclotron in the middle that's producing protons up to 30 MeV. It's low energy, but reasonably high. Okay, and there is an R&D room that's completely empty, like this. Okay, there's protons coming in here, and they're coming out like your hair. It's really thin and long, and so they said, okay, we put in a proposal with this team together, and we're now building the first space irradiation facility in Turkey. Okay, I got a grant of about 6 million Turkish liras from Kalkınma Bakanlığı this year, and I'm working on building this. So it was all because the Turkish membership to CERN happened, and here is my CERN partner, Bilge Demirköz, Greek guy, wonderful Greek guy, who's helping us with CERN partnership to build this beamline. All right, and here's my team. All right, now gravitational waves. All right, as promised. So, gravitational waves. Any questions about this project, by the way? I hope that was fast enough. I just wanted to tell you what I'm doing. So I am a particle physicist who's really excited about dark matter, and now I'm doing something really useful for space program of Turkey. But one day, trust me, no effort goes unwasted. I will return back to dark matter. That's my word. Okay? I hope to maybe if we can convince our politicians that pure science one day will come back as a return, no matter what you do. Okay? We still have a long way to go to convince them of that. But I think it's worth trying, and I hope you will help me on the way. All right. So gravitational waves. Something that's good for nothing for now. When Faraday discovered, electricity, he was playing with electricity. He was in England, and he was playing with electricity, and he discovered, and he showed this light bulb and things to the Minister of Finance at the time in England. And he said, what good is it? I don't understand. I mean, yeah, it lights up, yeah, okay, but what good is it? Faraday said, well, I'm sure, Minister, that within a few years you'll be able to tax it. And I've learned that this statement is very true. So when somebody tells me, asks me, oh, what good is gravitation? I say, wait a few hundred years, I'm sure you'll be able to tax it. Maybe the wait might have to be longer, but at some point there will be some taxes on it. I mean, cosmic rays, there's a tax on it now, yeah? Cosmic rays makes, it's not a joke. Let me tell you, a simple gate, a simple, for example, BJT, bipolar junction transistor, it's very common, okay? In your cell phone, it's everywhere. It's a very common semiconductor element in all electronics. It just costs, sometimes it costs 10 cents, sometimes it costs a few dollars, but no more than $10, never. The cheapest BJT that's validated for space use, validated by radiation for space use, costs 200 euros. Okay? So it's again, you can tax it. All right? What good are cosmic rays? Well, now effectively there's a tax on it. There's money attached to it. Gravitational waves, wonderful. Dr. Einstein was right. Yes, Dr. Einstein was right. Okay, we're very happy that Dr. Einstein was right, because we're very sad still of the fact that he was wrong on many things. Most important, his biggest blunder was the fact that he thought that women were not intelligent enough for science. Yes, he was definitely not an equal rights person. All right. So gravitational waves. This is Einstein's. This is the only equation in my slide. So enjoy. All right. I'm not going to try to explain you this awful formula. It looks really short, but if you try to explain it, it takes about 10 hours. So I'm going to pass. I'll try and explain it. What Einstein said is that matter energy bends space-time. You've probably heard about this. All of you have heard about it. So we already know that a single black hole standing by itself already bends space-time. So what does bending space-time mean? So if there was a black hole here, okay? There's a black hole there. How do I go? I want to go towards the camera. I jump? No, I can't jump. It's three-dimensional. I mean, this is the thing. In here, we're going to try to make this, two-dimensional example of a three-dimensional object. But I cannot jump to higher dimensions, and I haven't discovered that one yet. So if I want to go across towards the camera, if there was not a black hole, I would just walk straight. Why would I walk straight? Because straight is the shortest distance between 2 points. All right? But when there's a black hole, there's a hole, I walk around the hole. Right? Why? Because the shortest distance is no longer straight, because I would have to go into the hole and out of the hole. And actually, in the case of black holes, going in is easy, going out is impossible. So I would have to go, around. I happen to think, actually, as light, I happen to think I'm still going straight. If you were to ask that photon, are you going straight? Yeah, I'm going straight. But it's not, because space-time itself is curved. So as long as you're concerned, your travel is concerned, straight. Okay? But we know that space, so it's a bit funny concept. This thing about how space-time curvature actually makes things shrink, but you don't see it if you're inside it. Okay? To an outsider observer, it shrinks. But if you're inside it, it's kind of hard to observe. So you need an object, you need an observer outside of you. Okay, so remember this. To discover gravitational waves, you by yourself cannot discover gravitational waves. You need another observer. Okay, that's lesson number one. So gravitational waves have been an international dream, really. They've been talked about since many, many years. When I was an undergrad at MIT, there was a huge team at MIT building LIGO. which is now the experiment that discovered gravitational waves. Okay? And when AMS, I learned in 2004 that it could not go to space, as I told you, I was pretty depressed. But the LIGO team was always more depressed than I was. Okay? The graduate students, generations of graduate students graduated without finding gravitational waves. We've been looking for gravitational waves for 20 years. Right? It's not something new. It's been the Turkish media, right? As if, oh, they just built this thing and then it just happened. No, that's not what happened. They've been looking for 20 years and they couldn't find it, but they didn't give up. They built a better detector and a better detector and a better detector and a better detector. Okay, they're now on version 6 or something. All right, there's been many versions. So again, in Hanover, Germany, there is a arm. In LIGO, there's an arm. In Hanford and Livingston, there's 2 arms. Virgo, there is an arm. In AGO, which is Australia, there's an arm. And Tama, Japan, there's an arm. So you always see that these detectors are like this. One arm and another arm at 90 degrees. Why? Why? So let's discuss. So what happens when 2 black holes merge? 2 black holes merge. 2 holes are merging. So first of all, they can't just fall into each other. Why can't they just fall into each other? Because it has to conserve momentum. All right, they first circle. Angular momentum has to be conserved too. Unless your center of mass and my center of mass are exactly lined up. If I'm offset by a bit, I have angular momentum with respect to you, and I will circle around you. I mean, it could happen that they fall exactly in, but it's just nearly an impossible configuration to have. All right? That 2 objects have no angular momentum with respect to each other. So they are turning, and as they turn, they are losing energy. All right? And as they are losing, I will talk about how they lose energy. As they lose energy, the radius shrinks, and as the radius shrinks, at some point they cross each other's event horizon, and poof, they're gone. Okay? They become 1 from 2. Right? So what do? They cause distortions of distances. Distortion of distance. Okay? Note the word distortion. So their strength is measured by strain, the fractional change distance. So if my distance changes with you, I look at how much. There was a meter, but now this meter is changed by the strain. Okay? And typical value of this distortion, what has been measured, is 10 to the minus 21. So say there's a meter between us. I measure the distance between us to better than 10 to the minus 21. And I see 1 part difference in 10 to the minus 21. So how big is this? How big is this? This is, if you take the whole Earth, it's 1/5 of the size of an atom. Shall I repeat that? Right. If you take the Earth, distortion is 1/5 of the size of the atom. For 1 atom. If you take the radius of the Earth. Okay, so that's tiny, tiny distortion. So why are the sizes of these waves so tiny? Because space is stiff. Right? It's not an elastic object. Space is stiff. Right? And gravity only attracts, never repels. Have you ever seen gravity repelling? Have you ever seen gravity repelling? Gravity always attracts, right? There's an attraction between us. There's an attraction between you, and you, and you, and you. Right? We are all attracting each other. Do you see? Do you feel it? No. You don't feel it. But you only feel it when, well, what happens? When the whole Earth pulls you, right? Otherwise, gravitational also affects you. There's a gravitational pull between you and this table, but you don't feel it. Right? You don't feel the gravitational attraction of your friend. But when the Earth pulls you, you feel it because the Earth is very big and it's proportional to mass. Okay? And this shows you that gravity is actually very weak. But how do we know that gravity always attracts? you've never seen it repel. What if there is anti-gravity? What would it mean? What would it mean there is anti-gravity? Like you would float, right? The Earth would repel you. You would float up. Okay? Now, for all the particles at CERN, we measure their masses. Right? How do we measure their masses? We measure their inertial mass. Inertial meaning, what does inertial mass mean? It means m is equal to F divided by A. Mass is defined by how much force I need to push you to accelerate you. Okay? The formula is not F equal to ma. The formula is m is equal to F divided by A. That's the definition of mass. Alright? But there is gravitational mass is something completely different than inertial mass. Gravitational mass is how much you interact with gravitation. And until now, we haven't seen this at the particle level. We have not actually measured, besides heavy elements, how much gravity actually pulls them. And one of the things that now CERN is trying to do is measure, you know we haven't produced anti-hydrogen. You've probably heard about this, right? That CERN produces antimatter. That we produce angels and demons, right? Everybody knows about angels and demons, right? The movie. So we produce antimatter for the reason that we want to measure whether antimatter falls up or down. And this experiment will be done this year. They're now producing anti-hydrogen for the purpose of measuring. Because, really, anti-hydrogen could fall up. Maybe antimatter has the property of anti-gravity. Okay, so so hold your horses. It's a very interesting news that might come out of CERN. And if it does, well, you'll be able to float. Because I'm sure at that point engineers will take over and engineers will try to make floating devices with antimatter. All right? And we will probably be producing antimatter in mass stock. You know? We'll be stocking antimatter. All right, so until now, we only know, currently we know that gravity only attracts, never repels, and gravity waves have quadrupole polarization. Now this is going to be hard. So when you think about waves, I generally think about sea waves. Okay? These are waves in one dimension. Alright? But think about waves in two dimensions. Okay? The wave is going like this. At the same time, the wave is also going like this. Oh, you know one example, electromagnetic waves. Alright? But what does it mean that it has quadrupole polarization? It means the following. It means that it does this. That the area of this wave stays constant, but it does this. Yeah? So the wave here is going like this, the wave is, but it's there's a reverse. The phase is offset, okay? So it turns out if you do the math, and I've thought about it for a few days now, I cannot really come up with an intuitive way to explain you why gravitational waves are quadrupole. I'm sorry. If I come up with it, I'll tell you next year. Or find me in a few months or something. All right? And these are actually ripples in space-time. All right? Little waves that are flying through space-time. So, if it's a quadrupole wave, okay, you cannot just measure this quadrupole wave with one arm. You need two arms. You need to see that this arm is shrinking while this arm is expanding. Okay? So it should do this at 10 to the minus 21. Alright? So how do you measure it? You cannot just measure, take a ruler stick and do this. Well, we use light. But the light has to be completely decoupled. Remember, the system has to be completely, there has to be an observer. Alright? So we use light that's completely decoupled from the system completely. It cannot be coupled to any vibrations of the system. It cannot be there has to be vacuum, pure vacuum. Okay? So these arms, LIGO arms, what do? You take a laser, you put a beam splitter, and it goes there and back and there and back, and you have a photodetector here. Okay? It's somewhat similar, if you remember, to Michelson-Morley. Kind of similar. Right? It's called a Fabry-Perot cavity interferometer. Right? So where is my there? So what did they see? LIGO and Virgo saw the following. It had, and well, another thing is there's two of them. There's one in Hanford, Washington, and one in Livingston in, forget. I know that this is Washington. This is Louisiana. Yeah. All right. So they saw that the strain. Remember, the strain is how much distance is changing, and they saw there's Hanford data and there's Livingston's data, and they saw there just was. They saw this way, and this is really short. I mean, look at this. This is only from the beginning to the end of this. It's only 1/5 of a second. It's really fast, okay? It's this. You see two black holes, right? And you see this thing is going up and going down and going up and going down. What is this? This is two black holes doing this. Every time it goes up and down, it's one turn. When they join, they're actually going at 10% of the speed of light. Right? And these are not small objects we're talking about. Right? One turn around takes that long. 0.01 second. And they saw, what I find amazing, what I really find amazing about this, is that for years, there was this question, does gravity travel at the speed of light? Light travels at the speed of light, yeah. The famous question is always, if the sun disappears right now, how fast do you learn? How fast, I mean, does the Earth just go straight? Or does it continue going around for 8 more minutes? Right? The Earth is going around the sun. Does that information reach the Earth immediately? Or does it take 8 minutes? Now I know it takes 8 minutes. Because I can see that this data was shifted by 0.007 seconds. And that 0.00 seconds corresponds to the speed of light between these two detectors. Okay, so we learned so much from this. We learned that gravity travels at the speed of light. So how far was this merger? All right, how fast was this merger? Well, it was 410 megaparsecs away. The error bars are really large. It's really hard. You have two detectors, okay? And remember, they're doing this. Let me do it properly. All right? One of them is expanding the other one. All right? For 0.1 second, you have very little data, and they're trying to pinpoint where it is, okay, by where it's coming from, how fast, which angle it's coming. And the angle is also not very well, they think it's in the southern hemisphere. That's as much as they could gather. And the distance is about 410 megaparsecs. So what is it in light years? A parsec is what astronomers use, unfortunately. It's about 3 light years. So this was 1 billion years ago that this happened. Okay, 1 billion years ago, two black holes merged, and we've only heard it now. And when I say heard it, I'm going to actually make it you listen to it. Because what it is that this frequency is audible. And if we had ears that were precise enough, you would actually hear it. So I'm going to play it for you, actually. Why don't I play it for you? It's the audible range. And really, it is a pressure wave. Okay? It's strain. It's really distance changing. And what is sound? It is pressure. It is the air distance changing. The air strain. Air strain is pressure, and pressure is what your ears hear. Pressure wave. Okay, so this was actually sound, proper sound. Did you hear it? I don't know. important because they have sensitivity to different frequencies. So they have actually, it's again and again in different frequency bands. You hear that, Ian? Yeah? It's called a chirp now. Okay, it's a really famous. It's called a because what it's doing is it's going to higher frequencies. What's going on as the two stars are falling into each other? They're going faster and faster and faster, so the frequency is going higher and higher. So that's why it goes. Well, if you play it again, it'll only happen once. But listen. This all right? So that's really impressive. To me, to actually hear. I've heard. I can say, you can say I've heard two black holes merge 1 billion years ago, and we heard it. It's really out of the range. So the energy output of this event was 3 times the sun mass. So now, let's discuss the astronomers put everything into solar masses. How big is the sun? How big? Do you know the mass of the Earth? 1 million kilograms? 1 trillion kilograms? Trillion? Guess, come on. 10 to the 20 kilograms? 10 to the 30 kilograms? No clue. Okay, 10 to the 34 kilograms. Okay, that's the size, that's the mass of the Earth. 10 to the 34. What's the mass of the sun? It's 1 million times. Okay, the mass of the sun is 1 million times that of the Earth. So it's pretty heavy, the sun. Right? So the energy output is actually 3 solar masses. So what does that mean? There was two black holes. One of them had the size, one of them had the mass, one of them had the mass of about 36 times the mass of the sun. Squeezed them into about only 3 kilometers. Right? That's what black holes are, right? Enormously squeezed. The other one was 29. So what is 29 plus 36 make? 65. No, it made 62. All right? What happened? 3 solar masses were radiated as gravitational waves. Imagine that. So about 3 million times the mass of the Earth. 3 million times the mass of the Earth. So if you actually put that into watts, okay? Watts. Count in watts. It comes out to 10 to the 49 watts. Right? So if you wonder what 10 to the 49 watts is, so you might know that in the solar, in the Milky Way, okay, there is about 50 billion stars. And like and Milky Way is a reasonably sized galaxy, but it's not huge. Okay, the Milky Way is reasonably sized, but we know there are galaxies that are 1,000 times larger. Okay? In the universe, there are about, give or take a little, 100 billion galaxies. So if you were to kind of do this thing, you kind of go, okay, sun times 100 billion times another 100 billion stars. Give or take. Okay? And for that 1 second, the output of this one event eclipsed the output of the universe. For that 1 second, the output of this event eclipsed the energy output of the universe. This light curve. Which just blows my mind, really. It just, to me. So what I wanted to say is, here we are, we're now looking at something completely new. You know, we've only looked at the universe in light. We're just now learning to look at the universe in particles. And here is a completely new window, and I'm really excited about this. I think we're going to learn a lot about the universe and gravity. And I really hope we do, because gravity is something we, since Newton, we haven't really made any progress on understanding gravity at a deeper level. I mean, Einstein made a big stride, but now we have a chance to really get to do experiments on it and understand it. Right. So now the greatness is gone. Now let's discuss the ouch. What is it with the ouch? Well, electromagnetic theory. Electromagnetic theory says photon is both a wave and a particle. Right? Waves is easy to prove, particle is easy to prove, double slit experiment. And then quantum mechanics comes in and says, oh, actually all particles behave as waves. And particles. Right? Now, even the Higgs particle is a wave. It's really heavy, but it's still a wave. Alright? The big question, the day that this was announced, the phones at CERN were off the hook. Everybody wanted to know, oh, now that gravity has been discovered, gravity waves. And we know now that gravity is also a wave. Okay, we knew that light was a wave. You didn't know that gravity was a wave. Now we know gravity is a wave. But is gravity also a particle? It has a name. It has a theoretical name for many years now. It's called graviton. But this event, this beautiful event, so this is a wave. All right, who's engineering here? Okay, I will talk to them. Now I'm going to just take 2 minutes to talk to the engineers and physicists here. All right, you heard about dispersion relations. As a wave goes, how it changes with wave number gives you dispersion. Some people must know what I'm talking about. Please nod your head. Okay, good. So the dispersion relation actually gives you how fast the wave travels, and how fast it travels also can limit the medium it travels in. And the medium it travels in is the particle of nature. Alright? So we from the dispersion relation of this, because we know how far away it is, how far it's come, we know that it hasn't dispersed a lot, we can still see it. We can put a limit on the mass of the graviton.
You are not, it is not diffraction, huh?
Dispersion. Alright? And the limit is really depressing. How depressing is the limit? Well, okay, so the smallest particle we know, we have measured this mass. The smallest mass we have measured is 511 kilo electron volts, which is the mass of the electron. We haven't been able to measure the mass of neutrinos. We just know that it's somewhere along the milli-electron volt regime. And here comes along gravitons with their beautiful mass of at most 10 to the minus 22 electron volts, which is now the new frontier in particle physics. This is the smallest limit we have on any particle. And I don't know how we will ever measure or discover gravitons, frankly, but I just think it's a big ouch factor. So they were asking CERN to comment on this, and CERN did not comment on this, because it's just really depressing, right? So, but it's fun fact. It's beautiful. Not everything has to be done at CERN, you know? It's okay. we can lose this one. Fine. All right, that's it, I think. Thank you very much for your attention. I've taken more time than I was allocated, again. Sorry, Hocam. I'm sorry that I spoke for so long. I apologize that I took too much time.
I thought there may be some questions as well.
Questions? Any questions?
Everything is clear?
Maybe too clear.
Okay.
Complete the dark.
Yes, too much dark matter.
Thank you very much for a very exciting talk.